Let's quickly cover another topic, which is metric learning using neural networks. So there are situations where we are neither classifying nor doing a regression, but we are still solving a supervised problem. And those situations are where we know the relative order of some inputs, and we want to predict the order of another input, a test input, but we don't want to give it a very specific output. So an example would be a ranking problem. So let's say we have a ranking problem, right? So here what we have is we have xi and ri pair. We are given these pairs, xi and ri. Ri is a rank or some sort of a order of xi. So for example, let's say you have images and you want to rank them in the order of aesthetic appeal. Okay, so that could be one problem. The other problem could be a verification problem. So you have xi and xj, and we want to basically tell whether they are these two. If we try to find their similarity, then are they similar or dissimilar? That means either we only look at pair-wise combinations, and they are either 0 or 1. So 0 means they are not similar and 1 means they are similar. An example application could be face verification, where we have an organization that gives access based on face biometric, and the number of people in the organization keeps changing every day or every week and so forth, and because of that we can't have a recognition system where we have a fixed 1,000 classification because we have only 1,000 people, because tomorrow we might have 1,002 people, and then day after that we might have 998 people and so forth. So what we want to do is we want to maintain a database of a few images of each person, and given that the person is showing their ID and their face, we want to verify that is this the same person as they are claiming to be. So we want to take the test image and we want to compare it with the training images and see whether it is a same person or not. So it is similar or dissimilar. That is what we are trying to do. So here what is useful many times is to take this xi and predict the yi such that the yi is easily comparable. Now this xi, because it is an image or it could be something else, it could be a big vector or a big two-dimensional array, right? So this could be a two-dimensional array, but what we want is we want to change this into a yi and yj, which are very similar. These are low-dimensional vectors, so that we can simply take the Euclidean distance and see if the Euclidean distance between yi and yj is smaller than a threshold, then they are similar. If it is not smaller than a threshold, then it is not similar. Now here the challenge with doing this directly with xi and xj would be that you cannot take pixel-wise difference of images. That will lead to very poor results, because you also have background and you also have eye shades and so forth, or like the glasses, the frame of the glasses and so forth. So two people who have same red framed glasses are not the same, or two people who have the same skin tone or have the same background behind them when the picture was taken are not the same. So we cannot take pixel wise difference. We have to learn something called an embedding. So this yi is now an embedding, and that embedding has to capture this notion of similarity. So what is done in such cases is that we will take a neural network and we will give it an input xi, okay, and we will take the same neural network. Mind you that it is the same neural network, it's not a different neural network, and we will give it the input xj. Okay, so these are the same, and the output that we get is yi and yj. Okay, and then we will take their Euclidean distance, okay, or we will take their, let's say, we will put them in another few layers of a neural network, an additional neural network. So this is NN1 and this is NN2. Okay, and the output here could be 0 or 1 depending on whether they are similar or not, and the gradients will flow back through both NN2 and to NN1 both times, right? So it will, one will come from yi, the other will come from yj. So this is how it can be trained. So because we are using two instances of the same neural network, it is as if they are identical twins that are joined with each other, and that's why it's called a Siamese, based on the term Siamese twins. So this is a Siamese neural network. So there is also something called a Triplet Siamese, where instead of encoding whether xi and xj are similar or dissimilar, what we can say is that y of xi, okay, and y of xj are closer than y of xi and xk. Okay, so it's a triplet constraint. That means if we take two images of the same breed of dog, they are closer to each other than a third breed of dog, or a second breed of dog. So we can also formulate it as a triplet where I is the anchor, and then we have a positive instance which is xj and a negative instance which is xk. So closer than, okay. Okay, so in that case we will have a different kind of a Siamese, and the way that will work is that we will have the same neural network NN1, and it will share weights with another NN1, and it will share weights with another NN1, and the input we will give it is, let's say, xj here, okay, xi which is the anchor, and xk which is the negative sample. So this is the positive sample, this is the negative sample, okay, and this is the anchor, A for anchor, okay, and what will come out of this is yj and yk, and then what we will do is our loss will be a hinge loss over the differences, or over the Euclidean distance of yi minus yj and yi minus yk. Okay, so what we want is, so let's say we get these yi, yj and yk. Our loss is going to be such that we want to minimize okay, we want to minimize over max of, this is going to be a hinge loss. Okay, so whenever the distance of xi and xj is going to be larger than xi and xk, right, then we are going to penalize that. All right, so this is going to be, and if it is correct, if the distances are in correct order, then we are going to have no loss. So we are going to have a 0, comma, okay, so now we have yi minus yj, okay, all right. So this is going to be Euclidean distance, so I will use okay, and then yi minus yk. Let's write with more space. So yi and yj should be closer to each other. Okay, so we are going to, but if they are not close to each other, then we are going to penalize minus yi minus yk. Alright, and then just so that not all yi's collapse to 0, okay, they should not all collapse to 0. That's a trivial solution in which no one will have a loss. So we will have to add a margin here. Okay, so the margin is that it should be safer than a particular margin from this. Okay, so we will subtract that margin, or let's just call it delta, which is a hyperparameter, non-zero, greater than 0 hyperparameter. Right? And then we will sum this over all triplets. So now imagine if your yi minus yk is very large. Okay, it is very large, and it is at least delta larger than yi minus yj. Okay, then there is going to be no loss. Yeah, sorry, it's going to be plus here. Yeah, now this is correct. So we can use neural networks in that way also to do things like ranking or verification.